We are going to do quite a bit in this video, so let's not waste time. Lots of definitions in this course are going to feel somewhat clunky at first, and I just ask that you trust me. One of the things we talk about in geometry are things called postulates. Postulates are things we agree are true without proof. Another word for them are axioms. Postulates cannot be proven. We assume that they are true, and we work out geometry based on these accepted truths. Sometimes we get different geometries when we assume some of these postulates are not true. So we are working in what's called Euclidean geometry. Euclid was a Greek mathematician, often credited with being the father of geometry, rightfully so, because his book, The Elements, is the second most published book in the history of human writing. It is second only to the Christian Bible. So the geometry we study is called Euclidean geometry, and it is built on a postulate that says if you have a line and a point not on that line, there's exactly one line through that point that's parallel to the given line. That's called the parallel postulate. Postulate because it cannot be proven to be true. Human beings tried for about 2,000 years before they realized, you know what? Euclid was right. It's a postulate. Not something we call a theorem. A theorem is a statement that can be proven to be true using postulates and other theorems. You've heard the phrase Pythagorean theorem. That's because this is a statement that we can prove to be true for all right triangles in Euclidean geometry. So it is not just accepted as true, we can prove it to be true. Geometry is all about proof. Geometry is all about a logical system. Postulates, theorems are vocab words that you want to add to your math vocabulary dictionary. One of the terms you'll add to your math vocabulary dictionary is from the reading tomorrow in class called the ruler postulate. It's not that interesting, but we should have it in there. What it basically says is that you can put a ruler to a line segment, correspond those endpoints and all the points on the line segment to numbers on a number line, and measure a segment. What it gives us that's really important is this idea of betweenness. If you go to study math in college, and you take a geometry course in college, this is a very sticky definition. This is hard to define. We're going to have a very intuitive sense of it. We're going to say that when 3 points are collinear, you can say that one of them is between the other two, and we're just going to leave it at that. A, B, and C are all on a line. We can say B is between A and C. D, E, and F are not on a line, so we cannot say that E is between D and F. They have to be collinear points to use the definition of between. This definition in college is very hard to define, but it helps us get to something very important called the segment addition postulate. Again, postulate meaning we just accept this to be true. This should seem fairly intuitive. It reads, if B is between A and C, that implies that the three are collinear. Then AB plus BC equals AC. Said another way, if AB plus BC equals AC, then B is between A and C. If we look closely here, this part that follows the if is the same part that follows the then, and this part that follows the then is the same part that follows the if here. One way to write this mathematically is to say B is between A and C if and only if AB plus BC equals AC. When you have statements in geometry that go if blank then that, if that then blank, you can write them with one statement using an if and only if in between. We're going to come back to that later, but what's important is that you see this segment addition postulate and you write this down and you know it in both forms, or you know it in the form that I wrote down here. It seems like this is a no-brainer, but as a matter of fact, it's not. And it is something that we just have to assume is true. We cannot prove this to be true. But we can use it to do simple things like, if I tell you the distance from A to C is 20, and I tell you the distance from A to B is 15, you can figure out the distance from B to C. And if you haven't set it in your head, it's 5. And the reason we know that is the segment addition postulate, or SAP. Segment addition postulate. I actually prefer this, segment addition postulate. A little bit easier to know what it means than SAP. I've told you before in class, and I'll say it a lot this year, mathematics is very precise. It's precise in its notation, and it's precise in its language. When we write AB, we mean something different than when we write AB with a segment over it. This means line segment AB, and that is a shape. When we write AB, we are talking about the distance between 2 points. And when we talk about a distance, we're talking about a number. All year long, we will talk about this, and it's really important that we get this straight. When we talk about shapes in geometry, we say shapes are congruent. What we mean by that is that they are the same lengths. But when we say the lengths are equal, we have to write it as distances equal to each other. When we talk about shapes, we have to say they're congruent. It's not a perfect example, but I'll try. Think of segments or shapes like twins. They're the same shape, but they're not the same person. So that's kind of the idea of congruence. These are the same shape, but they're not the same line segment. They're different line segments. They just happen to be the same as one another. The distance from here to here is a number. The distance from here to here is a number. And we say numbers are equal. Another thing that we'll study a lot in geometry is an idea of a midpoint. And I bet you've heard that phrase before. It's pretty easy to probably figure out what it means by just breaking down the word. And segments, all line segments have a midpoint. Some point right in the middle that divides a segment into 2 equal parts. Anything that hits a segment at its midpoint is called a segment bisector. Those will be important terms for you to read about tomorrow in class and put in your math vocabulary dictionary. The midpoint is a point that is exactly in between the endpoints, exactly halfway in between the endpoints of the segment. A segment bisector is any geometric shape that can intersect a line segment at its midpoint. So you can have a line segment, AB, and you can have a segment bisector that's a line. You can have a segment bisector that's a ray. You can have a segment bisector that's a plane, as terrible as my drawings are, where this plane just happens to cut right through that segment. Anything that touches the midpoint of a segment can be considered a segment bisector. What we love to do in geometry is we love to put coordinates on a plane and find the midpoints using this handy-dandy midpoint formula. It's pretty interesting if you break it down. x1, y1 is some coordinate, x2, y2 is some coordinate, and the midpoint is x1 plus x2 divided by 2, and y1 plus y2 divided by 2. I always think of the midpoint formula as the average of the x-coordinates and the average of the y-coordinates. And that's how you find the midpoint. The easy example is when I give you 2 points and you just average them together. The hard problem, try this one on your own or see if you can work through it. The hard one would be something like this. I'll tell you A is the coordinate 3, 4, and B is the coordinate 8, 12, and C, I don't know the coordinates of x, y. And I'm going to say that B is the midpoint of AC. Try that problem. You could visualize this problem thinking about, okay, 3, 4 is about here, 8, 12 is about here, and C has to be somewhere out here. And you can think of, here's 3 and here's 4, and here's 8 and here's 12. So one way to think is I went over 5 and I went up 8. So I go over 5 and I go up 8. So this should be 13, 20. That's perfectly fine, and that's a valid way to do it. And that actually is the correct answer. I believe. I haven't done the problem yet. But I like to do it in a mathematical way to show my work. Here's what I know. 3 plus the x-coordinate of C divided by 2 has to equal 8. And 4 plus the y-coordinate of C divided by 2 has to equal 12. When you solve these two equations independently, you'll see that what you get is 3 plus x equals 16, so x equals 13. 4 plus y equals 24, so y equals 20. Do you see how I got the same answers in a mathematical way? What I like about this mathematical way, besides the ability to show your work and use some algebra, is if the numbers are not nice, this becomes a lot more difficult. The other formula you'll see in your classwork today, I almost hate to give you, because I don't even like thinking about this as a formula. I like using my brain here. We like to find the distance between things, and we like to find the midpoints of things. And so we were finding the distance, and now we're going to find the distance on a coordinate plane. So I'm going to show you an example, pretty easy one. So here's some xy plane. And I'm going to tell you this is the point 2, 2, and I want you to find the distance from 2, 2 to the point, how about 8, I want this to work out to be nice, 8, 10. So here is what you could do. I know that there's a vertical line or horizontal line that extends forever in this direction. And I know there's a vertical line that extends forever in this direction. And I know that all vertical and horizontal lines will meet at right angles. This line here has an x value of 2, and this line here has an x value of 8. What's the distance between here and here? 6. This horizontal line has a y value of 2, and this horizontal line has a y value of 10. That has a difference of 8. So the distance from A to B is the hypotenuse of a right triangle where one side is 6, one side is 8, so the other side is 10. That's a 3, 4, 5 multiple. When you look at the distance formula says the distance between A and B is equal to the square root of one x coordinate minus another x coordinate squared plus one y coordinate minus the other y coordinate squared. Now, one x coordinate minus one x coordinate is this distance 6, so it's just giving you a side of a right triangle, and then you would square it. One y coordinate minus another y coordinate is just giving you this distance, and then you would square it. You would add those two together and take the square root of it to find the hypotenuse in the Pythagorean theorem. So, yes, it's a formula we have, but I hate calling it a formula because it's just the Pythagorean theorem in the coordinate plane. Take a look at the following picture. Do you see that same idea of the Pythagorean theorem here? That this distance is always going to be the side of a triangle, and this distance is always going to be the other side of a right triangle. And now we have the hypotenuse squared equals this plus this. So the distance formula in your reading just has AB solved by taking the square root of all of this mess.